have a look at page 18. So for page 18, this is March 2017 P42. Okay, so for this particular question, define what is meant by gravitational potential at a point. This one, you can just make use of the definition from the notes earlier. It's actually the work done per unit mass to bring a small test mass from infinity to a point in your gravitational field. Okay, you saying work done to bring a small test mass from infinity to a point in the gravitational field is worth 1 point. You then saying that is per unit mass is another point. That's where your 2 points usually come from. So this one is just something that you need to copy from the notes. If you look at B, in B, they mentioned that a rocket is launched from the surface of a planet and it moves along a radial path as shown in the figure below. The planet may be considered to be an isolated sphere of radius r with all of its mass m concentrated as its center. So here, point A is the distance r from the surface of the planet, and point B is the distance of 4r from the surface of the planet. So all this is actually measured from the surface. Notice that they're not measured from the center of the planet. They're actually just measured from the surface of the planet itself. So in part 1, they want you to show that the difference in the gravitational potential between points A and B is given by this particular expression, where G is your gravitational constant. Okay, so if you now look at this question closer, they want you to find the difference in potential between points A and B. Okay, so they want to know what is the difference in potential between these 2 points. Okay, so in the first place, you need to first find out what is the potential at A, which by right should be negative Gm over Ra, because you should recall the equation for potential from your notes is negative Gm over R, and then gravitational potential energy is negative Gmm over R. So you want to use this form of your equation. So potential at A is negative Gm over Ra, whereas potential at B is negative Gm over Rb. Okay, so between these two, which one is actually the higher value? The potential at B is actually higher, whereas the potential at A is actually lower, because just now I kind of did mention to you, when you go further away from the center of your mass, main mass, your height is increasing, therefore your GPE is increasing, right? I could also kind of say that phi is also increasing now because they're both related due to the fact that GPE is equals to m phi. Okay, just now this one I wrote it there. GP is equals to m phi, right? Where GPE is proportional to phi. Okay, so they are closely related because phi is actually per unit mass of GPE. All right, so the difference between point A and point B in terms of potential will really just be you taking potential B minus potential A. Okay, so don't forget your negative. You will get negative Gm over Rb minus with negative Gm over Ra. So from there, before you go any further, you need to find out what is Ra and Rb. Okay, so your R here is actually the separation between the masses Okay, maybe I should kind of rewrite this. This is separation between the mass and point considered. This R here is separation between the mass and the point being considered. And then the U above the equation G negative GM over R, this one is separation between the masses. Okay. So they kind of mean the same thing, all right, in a way. So the GM over R here is separation between the mass and your point considered. Your RA is actually supposed to be from here to here. This one is your RA. So you see, it should be R plus R, giving you 2R. Then how about RB? RB should rightly be from the mass to the point that you're interested in again. This one is your RB. Sorry, maybe I should just draw it somewhere here. Okay, now maybe this one I just shift it down. This one I'm interested in the difference in potential between 2 points. This is changed in phi. My RB is from here to here. So from the center of the mass to point B, this one will be R plus 4R. This one will be 5R. Okay, so from there, you can now sub in to your equation below. So RB is 5R, RA is 2R. So try to simplify the algebra there. Eventually, you will get your answer as 3GM over 10R. Therefore, it's shown. Okay. So if anything, maybe I should modify what I just wrote here. Separation between mass and point considered. If you want to be a bit more specific, separation between center of mass and point considered for the second for this one, and then for the other one is separation between center of masses. Okay, so this one, let me just rewrite this. This one is just separation between center of masses. Okay, so this one is for the first part. Then let's have a look at the second part. So for the second part, let me just erase everything here. Now, in the second part, they mentions that a rocket motor is switched off at point A. During the journey from A to B, the rocket has a constant mass of 4.7 times 10 power 4 kg, and its kinetic energy changes from 1.7 terajoules to 0.88 terajoules. For the planet, the product GM is 4 times 10 power 14 Newton meter square per kg. It may be assumed that the resistive forces to the motion of the rocket are negligible. So use the expression that you've just found in B1 to determine the distance AB, to determine the distance from A to B. So let's just try and consider something like this. This one was your main mass just now. This is your planet. And then after that, you had 2 points to consider, point A, and then you have point B. Okay. So these were the 2 points that you are considering right now. So consider this, your rocket is moving from A to B. Say this one is your rocket, is moving towards B from A now. Okay. So what do you suppose would happen as it moves from A to B? Now, in the first place, when the rocket is at position A or position B, it will experience a gravitational force towards the planet. Okay, because your rocket is by right still under the gravitational field of the main planet, the main mass, it should experience a gravitational force towards the main mass. So the direction of your gravitational force should be towards the left. Okay, so this one is your FG pointing towards the left. Okay, whereas your direction of motion is towards the right. Okay, so what can I say right now as my object moves from A to B? If my object moves from A to B, notice that because my motion is towards the right, but my gravitational force is towards the left, what will actually happen is that my object will actually slow down. Okay, so number one, because FG and motion are in opposite direction, the rocket slows down, which is kind of consistent with what you're seeing here. Because you see, they told you that your kinetic energy changes from 1.7 terajoules to 0.88 terajoules. It's because you are actually slowing down when you're moving towards point B. So this one here, you will say that your CAIE is 1.7 terajoules. 1.7 terajoules. And then your KEB is 0.88 terajoules. Okay, so your object slows down, your KE decreases. This is what we know. Then after that, what can you say about your GPE? Because you're moving from A to B, you can kind of say that your height is increasing. Therefore, your GPE is increasing. Okay, so with these two in mind, what can you say now if you try to relate it to conservation of energy? According to conservation of energy, your decrease in your KE will be equals to your increase in your EPE. Okay, so far so good. Okay, so from that, finding the change in KE part is not an issue because you already have the KE values between these 2 points. How about the part where you want to find the change in your EPE? So just now I mentioned to you to find change in EPE. EPE at any point is just the mass times your potential. This is at a point. But to find the change in EPE between 2 points, you can take mass times change in potential. This one is between 2 points. And you coincidentally have found out the change in potential between the 2 points A and B here. Okay, so this equation can be further rewritten as change in KE equals to mass times change in potential, which is what you are actually doing here. Okay, so you try to sub in everything. For changes in K, take the higher energy value minus the lower energy value. So it's 1.7 minus 0.88 times 10 power 12 equals to the mass of 4.7 times 10 power 4 multiplied with my change in potential from the previous question is 3 gm over 10R. Okay, and then after that, if you try to look at the things a bit further, they've already also told you what is the value of GM. GM is this value, so you can just sub in this value straight into here. Okay, so eventually, if you keep moving to simplify your equation, you eventually will find out R is 6.878 times 10 power 6 meter. Okay, but this is not yet the end of your question. Okay, the question wants distance AB, you see. So if you're talking about distance AB, how much is distance AB? You look back at your question before this. Distance AB is this one here. This one is distance AB, isn't it? So distance AB, DAB is actually 4R minus R, giving you 3R. Okay, you can clearly see that because this is 4R, this is R, this one will be 3R. Okay, so what you have found was just R only at the end here. You need to go one step further to find out what is the distance AB, where you say is 3R. So equate it to 3R, submit the value of R, you eventually will get your answer as 2.06 times 10 power 7 meter. Okay, so this is how you will do this particular question. So if you're okay with that, then I move on to a next question. This one should be under page 5. So let me just go on to page 5 of your worksheet. So in page 5 now, what is mentioned is that you have a satellite of mass ms in circular orbit of radius x about the Earth. The Earth may be considered to be an isolated uniform sphere with its mass m concentrated as its center. For the first part of your question, A1, show that the kinetic energy EK of the satellite is given by this expression, where EK is equals to gmms over 2x, where G is your gravitational constant, and explain your working. So it may be a good idea to just somehow draw out your question here. So you have Earth, let's call the mass of the Earth big M, and then you have a satellite orbiting around the Earth. So this is your satellite right over here. Let's call the mass of the satellite ms here, according to the question. So it's moving in circular orbit around your Earth. Okay, so how are you going to find out the kinetic energy of the satellite? They want the kinetic energy of the satellite. So first thing first, to find kinetic energy is half mv squared. You could have applied it to your satellite here, but you need to find out what is your linear speed b first. Okay, so one of the things that you could probably do is something like this. Don't look at the written solution first, because this one I need to explain something else from there later on. So if let's just say I just wanted to use half mv squared to find out the kinetic energy of my satellite, what I could do is something like this, where I say that gravitational force provides centripetal force, because here I know that I have Fg, that Fg will be equals to my Fc. Okay, so here I will get Gmm over, sorry, maybe I shouldn't write as Gmm. I should have written as Gmms over x squared. I'm trying to follow the variables given inside my question. This one here is actually x instead of r. Okay, so I gmms over x squared equals to msv squared over x. These two x are the same, okay, right? So this x will cancel off. Then wait a minute, this x will cancel off, and then the square here will cancel off, and then this ms will cancel off. Eventually I will get b is equals to square root gm over x. Okay, so from there, if I substitute into here, ke equals to half mv squared, what you will get is something like this. You will get half ms, this one I should have written as half msv squared. This one you get k equals to msv squared. Half ms times your v squared. This one will be gm over x. So therefore, you will get GMMS over 2x. So this one is basically shown. Okay. You probably need to start with this first working first, then after that before moving to the second one here. Okay, this is a straightforward way of doing the question. It's actually this working here. Let me just highlight it in red. It's actually this working here. Okay, wait, it's actually this part here. Okay. The part where you are supposed to explain your working is the part where you need to say gravitational force provides a centripetal force. So therefore, Fg equals to Fc. Then after that, therefore, V is equals to square root Gm over R lor, because you are supposed to expand it from here. Gmms over X square equals to ms over V squared divided by X, giving you this. Okay, right? So this is one way of doing it, but there's also another different way of doing the same thing. Okay, this one would be actually this part of your answer here. This one you will do the same thing where you say that gravitational force provides centripetal force. So that you say Fg is equals to Fc now. So you get Gmms over X squared equals to msv squared over X. Okay. So from here, what you try to do is that you do something like this. Let me simplify further. You try to rearrange this such that you get msv squared equals to gm ms over X. Okay. So notice that this part of your equation is actually really close to your kinetic energy equation. You just need to multiply with half. So here what you do is that if you were to just multiply with half, you will actually get half ms v squared. You get half ms v squared equals to gmms over X. Then you say that since ek is half msv squared, therefore ek is gmms over X. So this one is shown. Okay, so there are two different ways of going about this. Either you do it this way or either you do it this way. Okay, but I prefer the first one. The first one is actually much easier to understand. The second one is a bit hard because you need to kind of like figure out the form to change it to CAIE. Okay, but this is actually the marking scheme answer. All right, there's another alternative one, which is the first one that I showed you. Okay, right. Then part 2 onwards was the one that we did not manage to do. So we'll go through that today. So, but before that, let me just draw some diagram here. This one here is your Earth. And then this one here is your satellite with mass ms. This one is your satellite. Okay. So your satellite is moving in circular orbit like this. All right. As your satellite is moving, you have a certain linear speed v, and that linear speed v is what causes you to have your kinetic energy. Your kinetic energy was already found here in part 1 as Ke equals to Gmms over X. So you consider the X as the separation between the masses. Okay, so now in part 2, you are required to state an expression in terms of G, M, and Ms and X for the potential energy EP of your satellite. So because your satellite is inside the gravitational field of the Earth, it would have gravitational potential energy. So here, you learned last week that GPE or U is actually negative GMM over r. So you're trying to use that same equation right over here, just that you need to change out certain variables to match what is given inside the question. This small m here is supposed to be ms. This r here is supposed to be your separation x. So eventually your EP or gravitational potential energy is supposed to be Gmms over x. So the negative sign in GPE is really important. Every time you write it out, please make sure you include the negative sign. Okay, because I explained to you last week, all values of GPE by right should be negative. Now, if you're okay with that, have a look at part 3. Use your answers in 1 and 2, the ones that you just did above, to derive an expression for the total energy ET of your satellite. Okay, so we know that your satellite here has KE GMMS over X. It subsequently also has GPE equals to negative GMMS over X. Your satellite has these two forms of energy. There's no other forms of energy here. So when you're asked to find out the total energy, the E total, is really just supposed to be the KE plus the GPE together. So that's why here your working is ET equals to EK plus EP. EK is this one, plus with negative GMMS over X. You solve for that expression there, you're going to get negative GMMS over 2X. So this is the expression for total energy of the satellite. Okay, so this is pretty straightforward. Okay, now if you then look at part B, this is the last part of your question. They want you to know this first. There are small resistive forces acting on the satellite that causes the radius of the circular orbit to change. Use the answers that you had in A to state for the satellite. Keyword here is for the satellite. Whether each of the following quantities will increase, decrease, or remain constant. Okay, so you are supposed to just focus your attention on the satellite itself. Okay, the energy of a satellite. If you're talking about the total energy of the satellite, because they already told you that there are resistive forces acting on the satellite, so what you can imagine is that as your satellite tries to move in a circle like this, in this direction, it encounters resistive forces that opposes its motion. Say at this point itself, you're trying to move like this, you will have a resistive force trying to oppose your motion, probably a resistive force R going like this. Okay, so when you try to move, you need to overcome the resistive forces. Work must be done to overcome those resistive forces. So energy must have been lost here. Therefore, your energy of your satellite must therefore be decreasing. Okay, so this one is for part 1. Because you know work has to be done against resistance or resistive forces, the energy of your satellite must therefore decrease. And now after that, you look at part 2. What do you think will happen to the radius of the orbit? Now, common sense will tell you if the total energy of your satellite decreases, chances are it won't orbit as high anymore. It will definitely orbit at a lower radius, so the radius must therefore decrease. Okay, so here I wrote that the total energy decrease, satellite won't be able to stay high in the orbit, it will come down to a lower radius of orbit. Okay, so this one is just using some common sense. And then after that, if you look at part 3, what happens to the GPE of the satellite? Because you can now think that if your radius or your height is somewhat lower now, your potential energy must therefore decrease. Okay, because last time what you learned in AS was that the higher your object is, the more is GPE, right? And then the lower an object is, the lower is GPE. So you can apply that same concept here. Your satellite is at a lower radius of orbit now, is at a lower height. So its GPE must therefore decrease. Okay, so the last part would need you to state what happens to the KE then. So if you want to state what happens to the KE, you can kind of apply conservation of energy for these two energies, potential energy and kinetic energy, because you know that potential energy is decreasing, kinetic energy would therefore increase. Okay, so this is the changes that are occurring. Now in your question, you are really just supposed to state what happens to the energies. You are not really required to explain. Okay, it's not a state and explain question. This one is just a state question. So you don't need to kind of like explain why certain things are like they are. All right. So this one should be okay, right? Here for the last part, part 4, I mentioned that by conservation of energy, the potential energy is decreasing, the kinetic energy must therefore increase. Okay. Now, there are also other ways of looking at this by using the expression in part A that you've done, but this one is actually going to be very tedious, all right? A lot of times people just don't do the analysis from the equation. You can just use common sense here, all right? So the more detailed, tedious analysis, that one, I'll just skip that one, all right? If you want to read it, if you want to know in detail what it is, you can actually read the explanation here, okay? So if that one is fine, let me move on to another separate question. The next one should be page what? We did page 5. Next one should be page 33. Let me have a look at page 33. Okay, next question that we can do is under page 33. Okay. So page 33, this is March 2019 P42. We have a look at that. Okay, so here in A part 1, define what is meant by gravitational potential at a point. Okay, be very careful about the terms they use. There's a difference between gravitational potential and gravitational potential energy. Okay, here they are really just talking about potential only. So when it comes to the definition, you would just say it's work done per unit mass to bring a small test mass from infinity to a point inside your gravitational field. So this one is usually allocated 2 marks. If you say work done to bring a test mass from infinity to a point in the gravitational field, this is 1 point. And then you say per unit mass, this is where your other mark comes from. Okay, so this one is pretty straightforward. And now in part 2, use your answer in 1 to explain why the gravitational potential near an isolated mass is always negative. Okay, so this one was something that I mentioned a fair bit in the last lesson. This one, I'll just elaborate it briefly. If you have a big mass M here, and then you have a distance at infinity here, if you were to place a mass, small test mass, right over here, we will normally tell you that your GPE is 0 or your potential is 0, isn't it? The reasoning is because we told you that here at infinity, you have no gravitational force, no capacity to do work. Therefore, GPE by right should be 0. Okay, and potential should also by right be 0 because it's GPE per unit mass. Okay, so now if you are interested at a particular point inside your gravitational field, let's just say you are interested at this point, which is a distance r from your main mass. Consider this, you want to bring that test mass from infinity all the way to this point here. Okay, so let's just see whether there's any existing force acting on the mass. By right, there should be an existing force acting on the mass, on the test mass. We know that gravitational forces are attractive by nature. So if at this point here, I consider a distance slightly less than infinity, there should be a gravitational force acting on it. This is at a distance slightly less than infinity, okay? And then if I go closer towards the mass itself, I definitely have a gravitational force acting on it. So you see, if I wanted to move from this point all the way to this point, I don't really need to purposely apply some sort of force to push it from infinity all the way to this point. There's already an existing gravitational force acting on the mass, so I can just let the mass move by itself, okay? So in my case here, when the mass moves by itself due to the existing gravitational force acting on the test mass, I could say that work is done by the mass. Okay, so when work is done by the mass, your GPE has a tendency to decrease. All right, Now consider this, if my GPE at infinity is 0 and then I go this way, my GPE drops, chances are the GPE here would therefore all be negative, isn't it? Because I'm decreasing from 0 value. When I have something decreasing from 0 value, it will go into the negative value already. Okay, so this is the reason why we will tell you that your GPE is always negative. Okay, so the explanation for this usually involves 3 main points. The first thing you will have to always say is that gravitational potential at infinity is 0. Okay, the second thing you will have to say is that gravitational force is attractive. And because gravitational is attractive, that's where you get your third point, where you say that work is done by the test mass as is brought from infinity to the isolated mass, from infinity to the isolated mass. So therefore, causing a decrease in potential energy. Okay. So after that, if you want to make more sense out of that statement, you can actually state something like this, but this one is not given any credit. You probably would just say that GPE decreases from 0. Therefore, GPE becomes negative. Okay. This last statement here is not credited. Okay. It's meant to further explain the first 3 points that you have above. Okay. So these 3 points here are pretty standard inside your questions. They do come up quite often. All right. So whenever you see this kind of question, just remember the 3 points. Gravitational potential at infinity is 0. Gravitational force is attractive. So this causes work to be done by a mass as is brought from infinity. Therefore, you will have GPE decrease. Your GPE would therefore be negative. Okay. It's really this point, and this point. Okay. Right. So hopefully that is clear. Okay. Then after that, you move on to part B. Now for part B, you have a spherical planet that has mass 6 times 10 power 24 kg and a radius of 6.4 times 10 power 6 meter. This planet may be assumed to be an isolated mass in space with its mass concentrated at this center. You have a satellite of mass 340 kg in circular orbit about the planet at a height of 9.9 times 10 power 5 meter above the surface. Okay, so this one, just be careful of that. You are at a height of this much above the surface. All right. So for the satellite, show that its orbital speed is 7.4 times 10 power 3 meter per second. Okay. So if you had a planet here, and then you had a satellite here that is trying to move in circular orbit about the planet itself, like this, we know that it has a certain linear speed v. Okay, we know we are talking about the linear speed because you see it's in meter per second. Okay, so you're talking about the linear speed here. That time I show you the derivation where you always say Fg equals to Fc, such that you get gmm over r squared equals to equals to mv squared over r. Then eventually v is square root gm over r. Okay, this is your linear speed, isn't it? Okay, so now they want you to show that the linear speed or orbital speed is actually this value here. Okay, so if you remember this equation straight, you can straight away apply it right over here. Okay, now in the workings that I've written in the book solutions, you will notice that I actually try to derive it out, where I just basically say gravitational force provides centripetal force, Fg equals to Fc, so you get gmm over r squared equals to mv squared over r, eventually giving you this. You don't need to show this. Okay, this one is not required. This entire thing is actually not required. It's just that I have a tendency to keep showing the derivation. All right. If you already know the equation itself, you can just straight away apply that. Okay. So, but when you want to apply it now, you just need to be careful because there's a trick here inside your question. They give you some values right over here where they tell you is 9 times 10 power 5 meter. This is not the separation between your masses, okay? This is just the height of your satellite above the surface of your planet. So to have a better idea of what this one is, when you're talking about your R is referring to the separation of your masses, the center to center separation of your masses. So it's actually referring to this. This one would have been your R, okay? This is the R that you need to find. But when you look at this question here, they told you this value of 9 times 10 power 5 meter is actually the height of the satellite above the surface. So you're talking about something like this. This is the height above the surface of your planet. This one is 9 times 10 power 5 meter. Okay, so this is 9 times 10 power 5 meter. Okay, you still need to add up the radius of the planet in order to get your totals, in order to get the separation between the masses. They did give you your radius of your planet right over here. They told you 6.4 times 10 power 6. So if you were to add your radius out, your radius is 6.4 times 10 power 6 meter. You need to add this and this to get you your R. Okay. That's why here when you look at the equation, B is square root GM over R, when you sum in the values, the R here is actually 6.4 times 10 power 6 plus with 9 times 10 power 5. Because you're supposed to get the separation between the masses. Okay. And then the rest of the values there, G, you can just get from the data sheet, second page of your exam paper. And then the mass is the mass of your planet, which is this one. So everything in, you should be able to get the answer 7.4 times 10 power 3 meter per second. Okay, so this one is pretty straightforward. Okay, then I believe there's another part to this question. Okay, so in part 2 of your question, they ask you to calculate the gravitational potential energy of your satellite. Okay, so find out the GPE of your satellite. They're not asking you to find potential, they're asking you to find GPE, right? So GPE or U is negative GMM over R. So you just use that equation. You already know all the relevant values, the gravitational constant, the mass of the planet, the mass of the satellite, as well as the separation between the masses. Same thing as before, add up the two distances so that eventually you will get your answer as negative 1.86 times 10 power 10 joules. Okay, then last part of your question, the rockets on the satellite are fired for a short time. The satellite's orbit is now closer to the surface of the planet. So right now, this satellite here is nearer to your planet. It's now somewhere around here maybe. Okay, somehow shifted to here already. All right. So you're supposed to state and explain the change, if any, in the kinetic energy of the satellite. Okay. So if you want to explain the change in kinetic energy of the satellite, you can make use of the equation V is equals to square root GM over R, because this one is talking about the linear speed of your satellite, which then gives you your KE. So you look at the equation V is equals to square root GM over R. You will say that the V, specifically V squared, is actually inversely proportional to R. Okay, I mean, if you just look at this equation, it's going to give you V inversely proportional to square root R. But then you square both sides, you're going to get V squared inversely proportional to R itself. Okay, so it doesn't matter which form you use now, either one is fine. So what you're really interested to know here is that when you are now closer to the surface of the planet, this means that your R has decreased. The separation between your masses has decreased. So when separation between your masses has decreased, your velocity by right should increase. Therefore, your CAIE should be increasing. Okay, so you just say that your R is smaller, your B is greater, therefore your kinetic energy increases. Okay, so just like that. Right, so if we look at page 30, it's still talking about potential again, but this time we are talking about something a bit different. So what is gravitational potential? We're just going to skip that because we've already gone through two of these kind of questions before. What we want to look at is part 2. Suggest why for small changes in height near the Earth's surface, gravitational potential can be considered to be approximately constant. Okay. Now, why can we say that potential is going to be constant for small changes in height near the Earth's surface? All right. All right. This one is more related to the equation itself. We know that GPR potential is negative GM over R. So let's consider a planet like what we have here, drawn here. This is a planet. If you're talking about the surface of the planet, maybe I zoom in just to get zoom in. If you're talking about the surface of the planet, right over here, let's assume that your center to center distance is going to be R between the center of your planet and the surface that you're considering. So let's call this position A. Now, if we have small changes in height near the Earth's surface, that would mean that we have to go a short distance of h. So let's just say that we go a short distance above the surface of the planet, a distance of h. We now end up with point B. Okay, so what we're interested in is point A and point B. Now, for position A, our potential there will be negative GM over R. At position B, our potential there will be negative GM R plus H because we want the center to center distance. Our center to center distance will actually be this one, R plus H. Okay. Now, because in the first place, we're talking about small changes in height, because H is so much smaller compared to the radius of your planet, compared to R, this one is your radius of your planet. Okay, because your height that you consider is so much smaller than the radius of your planet itself, we will actually be able to say that R plus H is actually the same as R itself. Okay, what do I mean by that is if let's just say I give you a certain value to look at. Let's just say H is just 1 meter, but I tell you R is 1 million meter. So if I ask you R plus H, it will just be 1 million and 1 meter. Okay. If I try to go and write them out in scientific notations, R itself was already going to be 1 times 10 power 6 meter, okay, 1.00 times 10 power 6 meter. So R plus H, if I go and write it in the same form for the scientific notation, it's just going to be 1.00 times 10 power 6 meter. This little one that you have here is not even going to register. That's why I can say that R plus H here will be the same as R itself if H is so much smaller than your R. Okay, so if your R plus H can be considered as the same as R itself, this equation here, negative gm over r plus h, can actually be the same as negative gm over r. So you do a comparison between these two equations, they're actually going to be the same. Therefore, phi is constant. Okay, that's the understanding here. Why we can say that your potential is approximately constant for very small distances above the Earth's surface. All right, this is you explaining from an equation point of view. All right, so your answer will be something like this, where you say here, phi is negative gm over r, gravitational potential phi is inversely proportional to your radius r. Now, near the Earth's surface, your change in height h is very much smaller than radius r. You have the keyword much smaller. Thus, r is approximately constant. So phi is approximately constant. Okay. This thing here would only make sense if you have this diagram to kind of refer to. If you just look at the explanations by itself, it kind of doesn't make sense. It has to be related to this diagram. Only then does it make sense. Okay. Okay, so part 2 I think should be okay. Then we move on to part B. All right, now for part B, this one is talking about escape speed, which we just did towards the end of the last lesson. We tell you right now, the moon may be considered to be a uniform sphere with a diameter of 3.5 times 10 power 3 kilometer and a mass of 7.4 times 10 power 22 kg. A meteor strikes the moon, and then during the collision, a rock is sent off from the surface of the moon with an initial speed v. Assuming that the moon is isolated in space, determine the minimum speed of the rock such that it does not return to the moon's surface. Explain your working. Okay, so what the question here is basically trying to mention here is that you have a moon, a meteor strikes the surface of the moon, causing a rock to be sent flying off. Okay, now they want you to find out what was the minimum speed of the rock so that this rock can just keep on flying off to infinity and not return back to the surface of the moon due to its gravitational pull. So this one, you know, is talking about escape speed. They want the escape speed here. Okay. So your goal here is to find out the escape speed. Now, because I see that this one is 3 marks, and then I see that you have explained your working, I don't think it's wise to just straight away sub in your escape speed equation. Okay, you just straight away sub in your escape speed equation. This is what you're going to end up getting. All right. So for your case, I think it'll be better to just derive it out. Okay, so in my case, you notice that the working here is deriving out the escape speed equation. So the derivation last time I mentioned to you, as your object is trying to escape, you have losses in KE as well as gain in GPE. So they're interrelated with each other through conservation of energy. You will have half mv squared minus 0 equals to 0 minus negative gmm over r, eventually giving you v equals to square root 2 gm over r. All right. So from here, you just sum in your values that you know from the question. V is 2 times g times m times r, divide by r, sorry. Your r here is actually 3.5 divided by 2 because you are given the value of diameter. So you need to divide by 2. And don't forget to change your units to meter. So from here, you will eventually get your answer as 2.38 times 10 power 3 meter per second. This is your escape speed. Okay. Right. Yeah, from what the marking scheme actually indicated, it seems like you actually don't need to derive it. because from what I can see, this one is a B1 mark. The B1 mark actually is you writing this equation for escape speed. Your C1 mark is you subbing in the correct values. Your A1 mark is you having the correct answer. So in your case here, actually, even if you didn't derive it and you just started off with the equation, you will still get your full marks. But for me, most of the time, if I see that the marks allocated is quite a lot, and then they have that little statement explain your working, I tend to go through the derivation from the start, just in case. You never know. Sometimes the marking scheme can be a bit fussy. All right. Okay, now if you just let's look at page 29, okay, it was mentioned to you that a gravitational field can be represented by lines of gravitational field, okay? Now, when you hear mention of things like lines of gravitational force, like the ones that you're seeing in the question here, it's actually referring to your field lines, okay? Gravitational field may be represented by field lines, like what I mentioned in the first part of your lesson for this chapter. So state what is meant by line of gravitational force. State what is meant by a field line. Okay, what does a field line actually tell you? In other words, so if let's say I have a mass here and then I have some masses, the mass has a gravitational field around it like this, and it's directed inwards, like so. If I were to place a test mass right over here in the field, what will happen is that that mass would be pulled towards the larger mass at the center here. There's a gravitational force that is acting on the test mass that's pulling the test mass towards the larger mass here. Okay, so at the beginning of this chapter, I mentioned to you before that field lines can be used to represent your gravitational field, but the field lines themselves have a direction to them. And the convention is that if you want to determine the direction of the field, normally it will follow the direction of the force acting on a test mass that is placed inside the field right now. So in our case, because our test mass is this one, and the gravitational force acting on it is this one, is directed inwards. So our field lines must be directed inwards in terms of their direction. So here, when we ask you what is meant by the field line here, what does your field line actually tell you? You can actually say a number of things. You can actually say, number one, it indicates the direction of force on a small test mass, or it will also be correct to say that it indicates the path in which a small test mass will move, because the force is directed inwards, so obviously the object will move inwards. Now, in some variation of the same question, sometimes the force may be replaced with another different term called acceleration. Okay, it indicates the direction of acceleration on a small test mass, which is actually kind of true because this Fg is your resultant force. The resultant force in turn causes an acceleration. So if you learn in dynamics AS, we mentioned to you before that resultant force produces an acceleration and that the acceleration must always be in the same direction as your resultant force. So it's actually correct to say so also. It tells you the direction of the force, it tells you the direction of the acceleration of a test mass inside the field, or also the path in which a test mass will move. Okay, so this is what a field line actually means. Now, if you look at part 2, part 2 is saying that by reference to the lines of gravitational force near the surface of the Earth, explain why gravitational field strength G close to the Earth's surface is approximately constant. Okay, so when it comes to your questions of gravitational field, sometimes you may be asked to explain why certain things are constant. If you look at page 30, which you did in the last lesson last week, page 30 was talking about suggest why for small changes in height near the Earth's surface, gravitational potential is constant. So that time we went through the process of looking at the equation where we say that because the small change in height is very much smaller than the radius of the Earth itself, your R plus H is actually equal to R itself. So actually, if you compare between 2 points near the Earth's surface, the potential will just be constant. Okay, so that was what we did in the previous lesson. Now here, if you look at page 29, they're kind of asking you the same thing, but it's for a different quantity. They are not asking for you for gravitational field strength. The one previously in page 30 is asking for your gravitational potential. So just to recap, gravitational potential was negative Gm over R. When it comes to gravitational field strength, it is actually Gm over R squared. Okay, that's the difference between these two in terms of the equation. The only difference is that there's a square term for field strength. So here they're asking you something similar. Why is it that near the surface of the Earth, the field strength is going to be approximately constant? Now, if you had tried to explain this in the form of an equation like you did in page 30, that one actually would be okay also. But here, the question actually mentioned to you by reference to the lines of gravitational force. So this one, you cannot use equation to explain. If I try to explain to you in the form of an equation right now, it will be the same as gravitational potential, where I basically tell you, if I have a point here, where this one is radius r, and then for a small change in height or close to the Earth's surface, let's just say at this point, this one is h. If I'm interested in 2 points over here, point A, maybe I should use a blue color here just to see better. If I'm interested in 2 different points, point A and point B, I can say that gravitational field strength at A is actually going to be Gm over R squared. Whereas gravitational field strength at B will be Gm R plus H squared. Okay, so the thing now is that H would be very much smaller than R. Therefore, R plus H is actually the same as R itself. So this one would in turn mean that GB is actually going to be the same as Gm over R squared. So when you compare between these two, they are actually going to be the same. So we can say that they're going to be constant. This is if you want to explain it in the form of an equation. But here, the question has really specifically told you to explain using your lines of gravitational force. They want you to explain in terms of your field lines. Why can we say that for very small height near the surface, we can actually assume that gravitational field strength is constant? Okay, so it actually kind of makes use of what we learned in the first part of the lesson, but I mentioned to you that field lines is a measure of field strength. Okay, I mentioned to you that field lines is a measure of field strength. I mentioned then further that the closer the lines, the stronger the field. Okay, that is the main thing here to refer to when it comes to answering this question. So let's just say, for example, I have the surface, this is the planet that I'm talking about. And then the gravitational field lines around it would be something like this. This is an exaggerated diagram. Like this, and like this. Okay, so this is how you would expect your field lines to look like for a planet like Earth. Okay, for example, the lines itself would be radial by nature, because one of the other things I also mentioned to you before this was that field lines are always perpendicular to contacting surface, to the contacting surface, or contact surface now if you would. Okay, they're always perpendicular to your contact surface. So my field lines must always be perpendicular to my contact surface. My planet itself, Earth, is assumed to be a perfect sphere. So the cross-sectional area will be a circle. So when you try to draw the field lines, it must maintain 90 degrees with the surface. So the end result is that it will appear to be radial, like what you're seeing here. Okay. So one of the things that you will be able to see is that if I were to go further away from the center of the mass, let's just say I go in this direction here, maybe I draw it in red. We'll go away from the center of the mass in this particular direction. What you're interested to see is how the line spacing actually changes. You can see that in terms of the line spacing, the spacing increases. Okay. By right, the spacing increase, therefore G should decrease. But here the question is really just asking you one particular thing. Near the surface of the Earth, meaning to say you're really considering only a small change in height above the surface. Let's just say, for example, you are really considering just this small h when compared to the large radius of the Earth. So that small h will be something like this. It's talking about this little area here. I mean, this little section here, which I highlight in orange right over here. Okay, so you're really just talking about this particular section here. Now, if you're trying to zoom in on this particular section, the thing is that when you zoom in that close with respect to how the entire field actually looks like, which is like this, the thing that you will notice is that when you try to zoom in at such a small distance, your field line, this, let's say that this is the surface of the Earth, zoom out, zoom in, your field lines probably look like this. Okay, so for this small distance of h right over here, the thing that people can say is that the line spacing appears to be almost the same. Okay, this one for our case here, we can actually say that the line spacing, that the line, the spacing is approximately same. Therefore, G is constant. Okay, for this small section of H, small height of H that you're considering, you will notice that the change in the line spacing is more or less negligible. The line spacing is actually approximately the same. Therefore, G is constant. That's what you're trying to explain here in your particular question. So your answer would probably be worded like this. First answer would be using that the lines of force or field lines are radial for a sphere like Earth, because in the first place, they must always be perpendicular to your contacting surface. This is where your first mark comes from. Then after that, you can actually just say, the second sentence, I think I need to go and modify it because it seems to be a bit too long. Actually, you don't really need to write this statement closer to the surface. You can actually just say that the height above surface is small. The height above surface is small compared to the large radius of the Earth, thus the lines are approximately parallel. The part where you say that the lines are approximately parallel is where your second mark comes from. Okay, but in the first place, you kind of need to explain why do you say that they're almost parallel in the first place. Why do you say that the line spacing is approximately the same? It's because the height is very small compared to the radius of the Earth itself. That's why I can say that they are approximately parallel. That's why I can say that this one is approximately parallel. Just like that. Okay. Then after that, you end with saying that parallel lines actually indicate constant gravitational field strength. Okay. For your marking scheme, whenever they say parallel lines, they always assume that the line spacing are equal. Okay, parallel lines here, they say the line spacing are equal, because for some people, they may argue that if I have something like this one versus this one, these four lines are also considered to be parallel. But then when I look at the line spacing, this line spacing versus this line spacing are not the same. So I cannot really say that the field strength is constant here, right? But here, for the purpose of your exam in the marking scheme, it seems to be that whenever they say that the lines are parallel, they by right assume that the spacing is equal. Okay, in case you're wondering. Okay, so to recap, these are the 3 points. No? Lines of force are radial for a sphere like Earth. Height above surface is small compared to the radius of the Earth, which in turn means that the lines are approximately parallel. Just these 3 points, sorry, these 2 points plus the last point, parallel lines indicate constant gravitational field strength. This will be the 3 points that you need to write. Okay, so that one should be okay. All right. All right, part B is actually referring to escape speed. Now, they tell you the moon may be considered to be a uniform sphere of diameter 3.4 times 10 power 3 kilometer and a mass of 7.4 times 10 power 22 kg. And the moon itself has no atmosphere, meaning to say it will not have any kind of air resistance. During a collision of the moon with a meteorite, a rock is thrown vertically up from the surface of the moon with a speed of 2.8 km per second. Assuming that the moon is isolated in space, determine whether the rock will travel out into distant space or return to the moon's surface. Okay, will that rock actually be able to escape all the way into infinity? So you can kind of visualize that this is the moon. You have a meteorite that somehow hits the surface of the moon, like so. And then after that, it causes a rock to be sent flying off with a speed of 2.8 km per second. So in the last lesson, it was mentioned to you before that for any objects to fly away into outer space without going back into the planet itself, you actually need to have a certain minimum speed called escape speed. Okay, so here what you really just want to do is to find out the escape speed and then compare it with the actual speed here. All right, so this one you probably could just use the equation for escape speed where VE is square root 2gm over R. Because here the question never really asked me to say explain your working, the derivation is probably not required. But although it's 4 marks now, okay, they gave you C1. C1 will probably be for the fact that they want to see that you know this equation. Square VE is square root 2gm. And then after that, the few subsequent marks will be for you subbing in your values. G is 6.67 times 10 power minus 11. Your big M is the mass of your moon. Your R is actually the diameter, the radius of your moon. But here you're given a diameter value. You need to divide by 2 to get the radius R. Okay, this is the radius. So you're given the value of diameter. Make sure you divide the diameter by 2 to get the radius. And then after that, this 10 power 3 here is you changing kilometer to meter. Okay, so just get all the values in. Eventually, you get the answer as 2.41 times 10 power 3 meter per second, but change it to kilometer. Meter change to kilometer, divide by 1,000. So eventually, you will get 2.41 kilometer per second. This is your escape speed. The minimum speed to escape all the way into infinity. All right, but you compare it with your actual speed right now. This is your actual speed, 2.8. This is the minimum speed to escape. This is the required speed. Okay, minimum required is this, but actual right now is 2.8. So the conclusion that you will be able to draw from this is that since your actual speed is 2.8 km per second, which is more than your escape velocity, the rock will therefore escape into distant space. Okay, so that is for this.